Oh, welcome to our new series simply called Why. Hello, I'm Bob White with Kollmorgen, and today on Why, we'll find out why stepper motors get hot. Someone applying a step motor for the first time may be a bit surprised that depending on how it is being driven, it will get pretty darn hot. In fact, it can get hot enough to cook an egg. All motors, whether servo, stepper, AC, or DC, tend to get warm. You are running electrical current through copper wire that has some resistance. This resistance causes the copper wire to heat up, much like the coil you have on your electric stove. For the most part, motor designers try to make the motor as efficient as possible. For example, with the least resistance as possible, but some losses must be expected. One interesting thing about a step motor is how you drive it. Most of the time, operating a step motor, you are applying peak current through the windings, not just when you run, but also when you stop and are sitting at idle. The longer the on time, the more the motor will approach its rated ultimate temperature. There are other phenomena that contribute to heating as well, including core losses due to the recirculating eddy currents in the rotor. If you followed our previous session on why, you also learned why step motors tend to be noisy. Noise associated from vibrations. Vibrations that in essence produce heat. And where does all this heat go? Since the copper is in the stator, the outer shell of the motor, this heat will dissipate from the motor casing into the air, as well as through the end bells and into the structure. The motor is designed to be able to run continuously with a temperature of about 130 degrees C, which is quite hot, hot enough to cook an egg, but we'll get back to that later. While a step motor getting hot is normal, it also may not be desirable in certain circumstances, and there are things you can do to help reduce heating. The best method is to utilize the idle current reduction methods provided in your typical stepper drive. This technique minimizes the current into the motor during idle motion, thus reducing heating. Other options are similar to what we've done to reduce noise, like basic wave shaping the voltages applied to the motor to minimize the harmonic content and to reduce the forcing function of the current applied. Microstepping also helps reduce heating. While the typical step motor may get hot, there are times when it can become too hot. Sometimes this may occur if a motor is mismatched with a specific drive with a parameter set that pushes the motor above its rated temperatures. We have tools that help determine the precise heating effects that a drive may have with a given motor winding. This tool predicts the temperature curve of the step motor to help guide you on the optimized selection of motor winding and drive parameters to meet your application needs. Oh, and back to the hot enough to cook an egg comment. We set this small skillet on the step motor when we started filming this video. It seems like it's warmed up enough now. Let's see if we can get a nice sunny side up egg ready for breakfast. So join us next time on Why, when we talk about why AC synchronous motors sometimes run backwards. Maybe a little salt and pepper?